everyone. Welcome to the video on mole calculations in chemical equations. So at this point we've looked at Avogadro's number, we've learned how to add up molar mass, and we've also learned how to balance equations as well as convert from grams to moles and moles to grams. Now we're going to take that further and we're going to look at our balanced equations and see how they have common relationships between our reactants and our products and how we can do calculations with our balanced equations. So a balanced chemical equation also tells us the number of moles of each reactant that combine to give us the number of moles of each product formed. Okay, so we have a common relationship between all of our compounds in a balanced equation. So if you look here, we have 1 mole of nitrogen for every 1 mole of oxygen, and that yields 2 moles of product of this nitrogen monoxide. Okay, because the coefficient out front is 1, okay, it's just there for emphasis. So typically we don't have to draw in that 1. Okay, but those are called mole to mole ratios. So I'm going to show you that on the next slide here. So the coefficients out front that we've learned how to use them and place them to balance equations, they form mole ratios. These can serve as conversion factors. So you've been learning so far that 1 mole is equal to Avogadro's number. That's a conversion factor, just like there's 12 inches in a foot. Okay, well now we can use our balanced equation and see a relationship between the compounds in that balanced equation. Okay, it has to be balanced for us to be able to do this. Alright, so if you look here, we can come up with mole ratios, and it just depends on what the question is or what we're comparing. But if you look at your reactants, you have 1 mole of nitrogen for every 1 mole of oxygen. So that is a mole to mole ratio. Of course, you could flip that over, still 1/1. Okay, for every 1 mole of nitrogen, you have 2 moles of nitrogen monoxide. And of course, you could flip that over. And then for every 1 mole of oxygen, you have 2 moles of nitrogen monoxide. So these are mole to mole ratios. So we can use these mole to mole ratios from the coefficients of our balanced equations to convert from moles of one compound to moles of a totally different compound. So this right here is so important and different from what we have been seeing. Okay, so far we've converted from grams to moles or grams to molecules of the same compound. Okay, so if you've been watching my series of videos, now we're going to use a balanced equation where we can relate one compound to a totally different compound because we have a mole to mole conversion factor or a mole to mole ratio. Okay, so these problems are similar to what we've been doing. We're converting, but we're just using different units, okay, and different conversion factors than what we're used to. Okay, so we always look at the problem. So we want to know how many moles of CO, so we're looking for CO, are produced from 3.5 moles of C2H6. All right, so as always, write out what you're given. 3.5 moles C2H6. All right, so that's what I always would do. I draw this, and I know that in the denominator, I have to have moles of C2H6. Okay, so now we've got to think about what's our relationship. How can we relate C2H6 and CO? Okay, these are 2 totally different compounds. All right, so the only way we can relate those is in a mole to mole ratio. Okay, so far this is the first time that our mole has been anything other than 1. Okay, it can be 1, but it can also be, whatever, 2, 4, 3, anything, because we're looking at our coefficients here, so whatever those are. Okay, so we're relating C2H6 and CO because that's what the problem is asking us. So here's our conversion factor. Here's our mole to mole ratio. So we have, for every 2 molecules of C2H6, we have 4 moles of CO. And then if we invert that, then that's the same thing. So we've just got to think about which way are we going to plug it into our equation. We're going to choose the one circled here because we need moles of C2H6 to be in the denominator. All right, so we wrote out what we know, 3.5 moles of C2H6. We know moles of C2H6 has to be in the denominator. And now we plug in our conversion factor that's our relationship between C2H6 and CO. Okay, so CO and C2H6 are totally different compounds, but they are related by the chemical equation. Okay, you have to be given the equation and look at the coefficients and come up with your mole to mole ratio. All right, so we cancel our unwanted units. We take 3.5 times 4, divide it by 2, and we get 7.0 moles of CO. And the unit that we want and the compound is left on top, not canceled out. All right, for practice, we have 3.5 moles again, so we have a balanced equation, and we have 3.5 moles of our iron 3 oxide. So I always start with what I'm given and plug it in. And now I look at what I'm comparing to. What am I looking for as my relationships? I'm looking for moles of CO, and I'm starting with moles of iron 3 oxide. Okay, so I'm looking for how am I relating my iron 3 oxide and carbon monoxide. So I'm trying to relate my reactants. So we're looking at how many moles of CO do we need to react with 3.5 moles of iron 3 oxide. Okay, and so I know that I have to plug in where my moles of iron 3 oxide is on the bottom. So here's a 1. So 1 goes in the denominator, and I have 3 moles of CO. Okay, if I plug it in opposite, the answer is going to be wrong because my units will not cancel. Okay, so I get the 3 and the 1. These numbers come from the balanced equation here. All right, 3.5 times 3 equals about 10.5. Okay, but since we start with 2 sig figs here, that's our measured number. And so we need to round that up. So we would say 11 moles of CO. So my unit here matches my unit here. All right, so this is showing you how to use mole to mole ratios from your balanced equation, okay, in order to relate moles of one compound with moles of a totally different compound. All right, I hope this helps.